Today we have the pleasure of hosting and being guested by Naomi Saphra. Naomi is a PhD student at the University of Sheffield, at the University of Edinburgh. Sorry, not my university.
It's on the slide.
Different university somewhere else that's also cold and grey. They study the emergence of linguistic structure during neural network training. And that ends up being at the intersection of linguistics, interpretability, formal grammars, and optimization. They have, kind of unsurprisingly, been called the Bill Hicks of radical AI critical comedy, and I'm really curious to hear who said that. Who said that, Naomi? Please, can you answer that?
You can actually find the original quote if you search that on Twitter.
All right, but without further ado, I will hand it over to you, Naomi.
Okay, hello. So I will be talking about learning dynamics of LSTM language models today, as you can see from the slide. Just a quick note before I begin, I didn't sleep well at all last night, so you have to give me extra presentation style points, and I'm going to be reading directly off of my slides more than usual. I'm a banana sundae split. Please do not eat. I am the emperor of banana sundae splits. Woo! Okay, so why are neural nets so effective? This is a question a lot of people are trying to answer right now. To start off, we have people who think, what happens during training? How does the bias get imposed during training? And they ask they use neural tangent kernels, they consider break-even points, they look at the actual loss functions and its landscapes, then other people are asking, how does an effective representation actually encode the linguistic structure that we need? So they end up doing interpretability stuff. They look at attention distributions. They look at the actual they look with challenge sets and stuff like that. A quick plug for a different paper from the one I'm talking about right now, which is an EMNLP 2020 paper that I have co-first authored with Thiago. That's a new way of probing. I'm asking a question that's at the intersection of these two questions, which is, how does the training impose bias towards linguistic structure in these models that we know are effective at learning language? So the particular question that led me down this rabbit hole I'm about to present to you is, why are local relations learned so much earlier? So first off, long distance patterns are less predictable. This is true. So it would lead this to happen. The gradient does take longer to propagate further, also true. And but the thing that I want to explore is the way in which LSTMs actually learn hierarchically. So to control for these first two issues, the gradient propagation and the long distance patterns being less predictable, I used a synthetic data set where I could control the frequency and the length of these relations. So you take a corpus with some vocab, sigma, and you randomly insert a rule, alpha, sigma k, omega. And so this intervening span could be unfamiliar given the rest of the corpus. So you're looking at, say, either Slithy, Toves, gyre, or blank. Or this could be a really familiar intervening span. For instance, if you're training on a Lewis Carroll corpus, then that green nonsense phrase actually comes from a Lewis Carroll poem, Jabberwocky. So then it would be actually familiar from the rest of the corpus, potentially. So what you end up with is two training sets, two test sets, where your two training sets are going to be either blank, or where the blank doesn't show up in the rest of the corpus and can't get memorized. Or you have it so that it's everywhere in the corpus and it's going to be memorized outside of the context of the rule. And then when you're looking at the test set, then you could be looking at either a new intervening span or the previous one. And we'll just get back to that as it unfolds. So why are local relations learned first? So the proposal I'm going to explore is that there's actually bottom-up learning happening in an LSTM. And what do I mean by that? I mean that you have these small constituents, and in order to learn a long distance relation, what the LSTM actually does is it learns an entire relation that is dependent on the constituents. It uses these known subtrees to build larger trees over them, that where it relies on the actual subtrees being familiar in order to build those relations. And this is a tendency. It's we look at then what happens when we train, and then we look at the performance on a test set that has the same intervening span, the Slavy-Tovs-Gyre span that we saw during training. So here our little dotted lines or dashed lines, they represent what happens when you have a familiar intervening span. So that's on the Lewis Carroll corpus. So in that situation, the model learns to accurately predict omega or faster. But the marginal probability isn't as high, probably because we see a lot of occurrences of Slavy-Tovs-Gyre outside the rule in that situation. So it can't rely so much on the intervening span being predictive. Meanwhile, in an unpredictable test set, so let's say this is either hoopsishly drangle me or, then that means that we don't get to see our same intervening span of Slavy-Tovs-Gyre, in which case you see that the Lewis Carroll corpus trained model actually fails to teach the general rule that associates these two endpoints, alpha and omega. Meanwhile, so we can see that when it memorizes that predictable span, it ends up relying on this whole phrase altogether and can't adapt very easily to a new domain. So step one in demonstration of this is that we can say that LSTMs trained with familiar intervening spans have poor performance predicting or from either without these familiar intervening constituents. Step one. So that's not enough to say bottom-up learning is happening. It might be that they're just never acquiring this either or rule at all, that they're just memorizing an entire sequence altogether. There's no hierarchical learning because it's just a chunk. Okay, well, to look at the actual role of the alpha either point, we are going to use a tool called contextual decomposition, which takes this entire sequence and can extract the linearized role of a single word. So we're going to approximate the influence of either on the probability that or comes up later. So, okay. So you can see from this thing is there's we can say that either is our relevant or in focus word, and we decompose the actual hidden state produced into a sum of the role of either and the role and anything that includes anything that isn't either, including interactions between either and everything else. Okay, so it's important to remember that this irrelevant component actually includes interactions that are the nonlinear interactions, the stuff we can't separate into a sum between this relevant word either and everything else. So what happens now? So we look again at this hooptiously drangle me setting where we don't have the actual where it performs really poorly, and we see, oh, wait a minute, it does acquire the rule. Even when it performs really poorly, it does have the rule. It just fails as it goes further in the span. And in fact, again, having the Lewis Carroll setting where you have predictable scaffolds, we learn the rule a lot faster. Okay, so yes, in fact, the either or rule is acquired faster with familiar constituents. Okay, so if we look back at contextual decomposition, though, there is this assumption of linearity built into it. This idea that you can take out the role of either and separate it from everything else. If you really take this to the extreme, then you would be saying it's just a linear sum. It's just word 1 plus word 2 plus word 3, et cetera, et cetera. And that's not really the assumption we want to make with language. We want to make an assumption that there is hierarchical behavior, in fact, that there is behavior you can't disentangle, that in this case that I'm showing you, trick questions is not something you can decompose into the role of trick and the role of questions, but that maybe you can decompose the role of Socrates from the role of trick, that those are definitions we can separate out more easily. And generally we can say there's a closer link in meaning the closer we're looking at the actual, the more close things fall in a syntax tree, actually. So to really formalize this concept, we have this idea of decompositional interdependence. So here we're looking at the difference between the isolated role of words A and B minus the isolated role of word A and word B separate. So that means that we're looking at the role of trick questions minus the role of trick plus the role of questions. And we normalize that so that it's actually a consistent thing. So then the more nonlinear the interactions are, the more closely associated we're saying those words are in the actual syntax tree. So this is something that tends to, so the nonlinear interactions do actually tend to decay across long distances. And so if you're looking at this, you also have to stratify by the sequential distance between things. But in general, it's true that there is a relation between proximity in the syntax tree and this and the nonlinear, the strength of the nonlinear part of the interactions between words. Okay, and if we actually look at that, we really do see that there is this strong interdependence between either and Slithy Tov's gyre in this synthetic corpus, in this artificial language. And there's not the same kind of strong relation that immediately emerges between them in the unfamiliar corpus, right? And so so it is something that gradually does emerge over the course of training in the unfamiliar scaffold corpus, because it's useful, but it's just something where if it has the opportunity to use this scaffold, it will jump right on it. Okay, so now we see that poor transfer performance is likely due to a high interdependence between either and that intervening span. So that supports this idea that there is an acquisition, that it tends to acquire hierarchical structure because it tends towards this bottom-up learning, and it uses the constituent as a scaffold supporting the long distance rule. Okay, so let's just go back and say, okay, you're talking about syntax related to this, but does syntax actually tend to align with this interdependence? Okay, we have to stratify by the non-syntactic factors because it is mostly dominated by sequential distance. And there is variation due to part of speech frequency. So we want to look separately at what happens in very predictable part of speech pairs, like a closed part of speech tag plus an open one will often be like something like the and a noun. And that's a really predictable common relation. So we might want to look at all of these things separately. And in fact, like there is a general trend. There is a general trend that is like, that is sequential distances that are closer tend to accompany these interdependence factors that are higher. And that's something that happens regardless of the part of speech classes, although it's stronger for some than for others. Okay, so takeaways from this, that language models do learn general input properties before they're task specific. Oh wait, this is actually something that also comes from another paper that I wrote, that but the bottom two, they tend to learn local dependencies before the long distance dependencies because they learn bottom up. So let's just take questions real quick before I go on to the bit of this that's the with friends bit, where I reveal all the secrets of how I ended up with this very strange sort of process of reasoning. Okay, now I'm going to talk about the actual process by which I ended up having to reorganize into this 4-point explanation that I have offered you. The actual process is much more convoluted because I came up with this question: why are close relations learned so much? And here's the picture I showed you before, where I had evidence from a previous project that long distance relations are learned much, much later. So let's say this is partly a result of the relative frequency of these closer and farther apart relations. But then I thought it would make sense if there's something hierarchical going on, because LSTMs are really good at this. Like the closer and farther relations, that would show up anywhere. But LSTMs have a particular affinity for at least right branching natural language, right? Okay, so what would it even mean to say they are building things hierarchically? So, all right, maybe it means they could take advantage of a familiar gradient conduit scaffold so that the model can build on that representation. So the model would learn faster with those gradient conduits, scaffolds. And then I figured, okay, I'll build an artificial language data set to test this out. I'm going to build one that has 2 training sets and 1 test set, which can match the gradient conduits in the training sets. And then there's 1 training set that allows it to memorize the gradient conduits and 1 that doesn't. And I really want to use this cool tool, actually, contextual decomposition, because it shows that, oh, wait a minute. Yeah, here we go. I want to use it because then you can see how the long distance rule would get learned. And so this picture is what happens in the, like this in-domain test set that I was talking about earlier, right? Where you see a really strong effect. By the way, I don't come up with a replacement for this term gradient conduit, which nobody understood until after the first rejection of the paper, which was completely like an esoteric explanation that did not have this nice 4-point structure that is already kind of difficult to convey, I admit. So scaffold is something that I only came up with as a word to use later. And suddenly people were a lot more willing to read through a paper that used the word scaffold than gradient conduit. Okay, so I bring all of this evidence to my advisor to start out, and he says, it seems like you're making a claim you could be testing more directly, which is like in my auto advisor script when I'm like, I think I've really come up with something here. Then I push the button that says, it seems like you're making a claim you could test more directly, because he's always right. So I say, oh man, I could just look at this without the contextual decomposition, which was the cool tool that I thought would be fun to use. Oh, but it is still true in my boring plot where I'm just actually looking at the prediction without the contextual decomposition. That's nice. It is still true that we're learning faster in this familiar domain. Okay, and contextual decomposition is still necessary, because it shows it's not just memorizing this whole thing all at once. And I bring this to someone else at Edinburgh, Amos Storkey, and I'm like, look at this cool thing. And he's like, I don't believe this. Contextual decomposition has some error. You need more evidence because the whole string is predictive. So what if you're getting some evidence that should be in the predictive, the scaffold, misallocated into the beginning? So I need to look at the unfamiliar conduit test set. But even in this setting, it's true that alpha can predict even without the scaffold, although not as well, because there is some misallocation in the approximation. It's true. Oh no, I kept forgetting that I had to account for vanishing gradients. Oh, of course you would acquire this alpha omega rule faster in your like familiar scaffold setting. Fine. Okay. Oh, and look at that. There's no generalization when you actually look at what's happening with the whole language model instead of contextual decomposition, because there's a real lack of evidence of so the lack of generalization now I realize, that is evidence that it's depending on the scaffold. Okay, that was what I was thinking. That was what I was trying to demonstrate. But there's so many moving parts when you're doing something like this, it's easy to lose track of any particular thing. So now I have to ask myself again, what did I actually mean when I said the long range relations will be dependent on the smaller constituents? It's something like this actually, where you have an incremental contribution as you go through the from the beginning to the end. Okay, so that's when I came up with this decompositional interdependence measurement to make it more like explicit what I am talking about when I talk about being dependent on a smaller constituent. Okay, so there is this very heavy interaction between alpha and the scaffold. So now I have to go back to natural language and be more explicit about this. And actually, I started out by splitting everything into these just parent, ancestor, and cousin sets and looking at that. And that was evidence, but I was like, oh, wait, you can actually be way more general than that if you're looking at just syntactic distance more broadly, as opposed to these smaller categories. Okay, and then I posted my really clear explanation of this process that I went through online, and someone cited it, and I had to send them an email asking them to update it because I need to pretend that my original version of this manuscript never existed because it's so esoteric, and I don't want anyone to read it when they could read my current explanation. So it's really confusing. Okay, so that's the process, since talking about your process is part of NLP with friends. So now, has that brought in any more questions? I've got 5 minutes to talk about what probing really tells us. When you're choosing a probe, that there is actually this spectrum where you have, on the one side, you have your mutual information. You have like, just tell me the information. And at the other extreme, you have, this is a very constrained structure, like structural claim I'm making, like this is a linear system. And then like, you can make it more or less constrained in terms of the actual model class that you're willing to take a probe from, right? So at the mutual information side, you have some advantages, but disadvantages. It's really hard to approximate, and it completely ignores the structure, which is probably what you're actually interested in when you probe. And also it's like if you're using an arbitrary decoder on your representation, then you actually are able to extract any information because it just has the information about the inputs, unless it's like some weird unigram representation. And then on the other side, you might be looking at like the attention distributions and stuff that you are actually able to analyze, but it's probably not going to be like true. Like most structural claims are probably not true, and that's annoying when you want to like publish a paper with a positive result. Clearly here I'm on the side of like generally structural probes are the best probes, but a lot of stuff is not structural. The worst things are when we see claims based on like a deep probe where you've learned a ton of parameters and then made like a claim using like a model that you have trained. It's not geometrically principled. It's not like you're making an information theoretic formal claim. And it's really unclear how to interpret any particular architecture. And also, you're probably not going to outperform random unigram vectors. And that's part of a previous paper that I published. I'm really attached to that rant, so that's why I brought you through it. The paper, by the way, if you really want to understand better what I have explained, the paper to refer to is my new LSTM's Compose and Learn bottom-up paper, which is an EMNLP findings paper.